Hello, everyone. Thank you for joining us. Speaking today, we have Jean-Lévy Baudouin, Averna's VP of Sales for Western Europe and Asia, along with test expert Martin Kruschel, VP of Sales and Operations for Eastern Europe. Before we begin, I would like to inform everyone that you will be automatically muted, but we will be answering questions near the end of our webinar. And with that in mind, let's begin.
Hello, everyone. I'm Jean-Lévy Baudouin, and I'm very pleased to have the opportunity to speak with everyone today. I've been working within the quality and automation for over 15 years, and as Amy mentioned, I lead the Western European sales team. I'm joined here with my colleague, Martin Kruschel. Martin, can you tell us a little bit about yourself?
Yes, thank you, JL. My name is Martin Kruschel, and I am responsible for Averna sales and operations in Eastern Europe. I've been involved in the test and measurement world since 2006. And for a better part of my career, I was serving the automotive segment, delivering test and validation systems.
Well, thanks, Martin. We're both looking forward to sharing Averna's experience in the EV testing market. There is currently a major shift in the car industry, which translates into a large increase in the number of electrically charged vehicle or ECVs being introduced. This is a demanding time for automotive manufacturers, and operations may require additional support to quickly increase production capacity while maintaining a high level of quality. So first, the objective is that I will quickly introduce Averna as a global expert in test, measurement, and automation. Next, we'll take a look at the latest European trends that we're seeing for electric and hybrid cars. Then we'll go over specific challenges that we're seeing in implementing an inline automated test solution for electric motors. We will be sharing a real-world example of a solution that we've deployed for manufacturing, but please note that some of those lessons can also apply to design validation. And finally, we'll open the floor to any questions that you may have. Now, looking at this slide, you see that Averna is actually a global system integrator, and we're providing solutions in the test and quality market. To support our global client base, we have 9 locations worldwide. Our corporate HQ is in Montreal, Canada, and which was founded in 1999. Today, as we've grown, we have offices across Europe, including the Netherlands, Belgium, and Poland. We have 2 offices in the United States, one on the West Coast and one on the East Coast. And finally, we have a build-to-print facility in Mexico. In Asia, we have an office in Japan and additional support coverage in China, Taiwan, and South Korea. So while this webinar is dedicated to the automotive industry and electric vehicles specifically, we routinely execute projects in other markets, including medical, consumer electronics, and energy, to name a few. Test is a requirement everywhere, and over the last 20 years, we've been exposed to a broader view on test and manufacturing and quality processes. This experience allows us to adapt best practices between industries. By having the insight and hands-on experience, Averna remains ahead of the curve from a technology perspective, and we've continued to grow. So this is a good summary slide of our complete capabilities as a system integrator. Averna offers solutions that range from Industry 4.0 consulting services over prototyping, semi and fully automated test solutions, all the way to asset assembly replication services or build-to-print. The majority of our business consists of designing, building, and deploying test and manufacturing assets at our customers' facilities or to our customer facilities. And in order to develop our solutions, we have more than 200 engineers in-house, and they're spread over various areas of expertise. They cover every aspect of tests, and that gives our customer confidence in meeting time to market requirements. I remember a project where we were able to scale up to 40 people, a team of 40 engineers and technicians on a project to reach a key milestone. Now, after the Paris Protocol was signed by the EU, there has been much talk about efficiently moving towards a carbon neutral society. And more recently, the discussion is shifting to the European Green Deal, This new agreement would bring an even more aggressive target for the deployment of electrically charged vehicles. The first element of an ECV is to charge it, of course, and you do this by plugging it into an electrical network, whether it's at home, at work, at the shopping center, or in a public area. In a study done by the European Federation for Transport and Environment in January 2020, they forecast the number of public charging stations available to consumers. You can see from this graph that the number of charging stations that will be needed in the EU is increasing significantly. And this graph only covers the public chargers, but of course we expect both the private and commercial sectors to invest in order to attract customers and employees needing charging capability. While Averna has experience in testing the charging section, this webinar will focus mostly on the vehicle itself. And as we're monitoring this market, we found some information that's particularly interesting. According to the European Automobile Manufacturers Association, the market share for EU and EFAT region of hybrid electric vehicles, HEV, and ECVs reached a combined amount of 22.3% in Q3 2020. If we look at the growth between Q3 2019 and Q3 2020, we've seen an increase of 211% for ECVs and 88% for HEVs within the EU car market. That's quite a significant year-over-year increase. Now, let's move to the basics of electrically charged vehicle. The car operates in two different modes. First is the mode while you're accelerating. In this mode, the motor needs to generate energy and will be requesting power from the battery system. Throughout this webinar, we will refer to this as the energy generation mode. So the second mode is when the driver is either decelerating slowly or braking. Here, the engine will try to transform the kinetic energy from the car back into electricity. And today we will call this mode the energy recovering mode. So Marcin will now introduce us to the different test concepts in the solutions. Marcin?
Yes, thank you, JL. So a growing demand for EV motors resulted in a customer turning our way to build a test system capable of validation for modern and newly developed EV motors. The test system had to meet a great number requirements. It had to be capable of spinning up to 20,000 RPMs, as the current trends in EV motor design are based on the efficiency which can be maximized by increasing the RPMs. It also needed to be capable of HV testing. Modern EV motors are powered with 400 volts DC, and the newest generations go up to 800 volts DC. The station must perform the HV test as a first step to ensure the motor's insulation is proper and that it will protect the end user, but simultaneously the operators at the production floor. The system also must assure full traceability, so in case of any warranty claims, the production data can be easily pulled out of the traceability database and used for rework and retest purposes. Additionally, the test station must include an integrated laser marking station to add traceability to the device under test, or the DUT if you will. Additionally, the system needed to be deployed inline as a part of an automated production line. As such, the test system's operation must be automated. In the presented case, the robot was responsible for handling the DUT. Naturally, the system should operate the DUT, which is, of course, the EV motor in our case, with the highest fidelity of its standard working conditions. The EV battery, typically lithium-ion battery or nickel metal battery, is capable of providing extremely high inrush currents that are directly responsible for extremely high torques being available to the user or to the driver from very low RPMs. To be able to provide that current, the system cannot just simply be powered from a regular landline. It also cannot be powered from a battery, as it would require constant recharging, rendering the system unusable or at least unpractical. The solution was to simulate the battery. An extra advantage of using a battery simulator is its capability to recycle the energy being generated during testing. We'll speak a bit more about it in the next slide. The EV motor also requires an efficient cooling system. At best, the system should use as little coolant as possible. To meet that, the system must also be equipped with a chiller, in addition to multiple fail-safe systems for protection. So, as you can see, there were many considerations. JL?
Indeed. All previously described requirements needed careful design consideration. However, we faced three main challenges throughout the course of this project. And those include, the first one is energy management, which also includes energy recycling. Then dealing with high-speed revolution of the duct itself and the driving motor, particularly transferring the high rev torque from one motor to the testing motors. And lastly, we had to consider the safety of the system to protect customers' investments. High voltage testing assures that the product qualifies for further testing and prohibits operators and the end user from electric shock. But the real danger comes from high revolution capabilities of the test station and the duct. Rotating a mass at 20,000 RPMs will generate high centrifugal force. And the rotated mass is not, if the rotated mass is not ideally symmetrical, unwanted vibrations are immediately generated. These vibrations can easily damage not only the duct, but the test system itself. So now that we presented the challenges, let's focus on the first challenge, energy management. Marcin.
Thanks, JL. Well, first, the electrical power requirements of an ECB motor are different than what a normal electrical network can provide. This requires a manufacturing test solution to implement a battery management system. One purpose of that battery management system is to accumulate energy from an external network and supply it to the test solution. This allows us adequately simulate the high and steep peak of electricity that is needed to test in manufacturing. But this also means that we were required to prepare the circuitry with high power components. This allowed the system to manage the high inrush current required to test different to test the different scenarios of motor acceleration. The main challenges here were to accumulate and supply energy, as we were dealing with high power components. Additionally, inside a car, the current draw normally remains in average range, but the test station needs to go to extreme. Therefore, we required an efficient energy source from the network and had to simulate a battery power system with a high and steep peak of currents. The way to test the kinetic energy is through integration of another EV motor in order to simulate the kinetic energy from of the car. Luckily enough, the energy harvesting and capturing can be realized with the battery simulator we use to supply the test system. In this case, it was a 250 kilowatt unit that was providing a good energy overrun margin, as the nominal power of the DUT always remains below 150 kilowatts. The solution had to be also bidirectional, which meant it must drive the DUT, but at the same time absorb and recycling the energy generated by the DUT. So to sum this up, in recovery mode, the system we designed now accumulates electrical energy from the network, drives that energy to the DUT, and circulates energy from the tester motor to the DUT. In generation mode, the battery simulator drives energy to the motor within the test station and circulates energy from the DUT. In our experience, in our practical tests, energy recycling can be upwards 70 to 75%, thus lowering the plant's electricity costs with a lower carbon footprint test solution.
Well, thank you, Marcin. The second challenge we'd like to discuss is high revolution coupling. Couplings are mechanical components used to connect two inline shafts to enable one to drive the other at the same speed. This is an effective interface between the DUT and the tester's driving motor. So Marcin, can you elaborate on what we did on the coupling side?
Sure. So, well, the coupling must be carefully designed to be able to transfer torque from the driving motor to the DUT and vice versa. So it must be bidirectional, also called a two-way. It must be so-called two-way clutch. The clutch must be capable of mitigating any vibrations being generated within the test system and provide near to perfect alignment between axes. Often these vibrations come from DUT. Working with 20,000 RPMs and 150 kilowatts motor requires an extremely reliable design in terms of rigidity and balancing to mitigate the vibrations between the spindle and the tester's motor. With this in mind, we carefully selected a coupling system to achieve the required 20,000 RPM. A clutch may be perceived as a mechanical interface between two moving subsystems, and in this case, the clutch must also transfer the torque between these subsystems. So how it was practically done? Here we can see the DUT nest. The nest is equipped with hydraulic clamping for rigid DUT fixation. You can see in the middle of the nest a spline hub. The hub is a mechanical connection between the DUT and the rest of the tester. On the right side, we see a driving motor. And the high revolution coupling that we speak about sits in between the two. The clutch itself is composed of three balancing rings, providing an easy and flexible balancing options, and two sets of transferring lamels. A lamel is a small collection of welded plates. Each set has 3 layers in this case. The lamels are the effective components transferring the torque while mitigating the vibrations and to compensate for any misalignment. And with this practical design, we were able to efficiently manage both issues simultaneously.
Cool, thank you, Marcin. Quite interesting. The last challenge we'd like to discuss is one of the most important one, which is protection and safety. We briefly touched on that topic earlier, and when we spoke about the high voltage testing. While the system safety is probably one of the most important issues to address, in this case, part of it was one of the easiest one. But Marcin will give us more information about this. Marcin?
Yes, so insulator tests are common and required equipment is readily available. So designing and adding the safety features was not the difficult part of this project, the HV related features. But what was challenging was designing a real-time vibration monitoring system with another redundant vibration monitoring system just as a backup. We said that the clutch was that the clutch we designed was supposed to eliminate any vibrations that may appear in the system. However, there is always a possibility that the vibration introduced by the DUT can be so high that the clutch system will not be able to mitigate it. In this situation, in the best case scenario, it is for the vibrations to be transferred through the spline hub to the clutch and then to the driving motor. As the motor is running its rotor at 20,000 RPMs, this will cause a permanent damage to motor's bearing and effectively put the station down. In the worst case scenario, a vibration could destroy multiple points within the system, and naturally this will result in a permanent damage of the test station. So to avoid these disastrous scenarios and to protect customers' investment, we equipped the station with multiple accelerometers located at each significant mechanical joint of the system. This meant, in our case, every fixed bearing. The accelerometers were connected to the DSA dynamic signal acquisition board, so the acceleration and deceleration signals can be acquired and analyzed in real time. We applied and normalized vibration levels corresponding to the system status. These include pre-warning, which is when testing can be continued by a trend must be observed. Warning is when the system should be shut down as soon as possible for a source of these vibrations to be identified and neutralized. And the emergency when the system must be shut down immediately. And in this case, most likely, all bearings must be inspected and replaced if necessary. So the secondary or the redundant system is visible in the current slide. It is less sophisticated than the previous one and acts only as a safety switch. It has one tripping level that, if triggered, immediately leads to an emergency shutdown. The system based on the the system is based on the contactless laser vibration sensor, and that secondary system shown in the slide has an independent embedded controller which assures maximum redundancy, increasing safety overall.
All right, well, thank you, Marcin, for this detailed explanation. I'm sure that our audience appreciated the information. To briefly summarize, the European market share for ECV and HEV cars has almost reached 25% in Q3 2020. This is a major increase over the numbers last year for the same period. With Averna's extensive experience in creating test solutions for both e-charging stations as well as the electrical powertrain of an ECV, we have identified several key challenges that must be addressed before being in a position to be competitive in this market. If you're about to jump into a new tester project, remember that there are solutions available to tackle these and also other challenges, of course. Some of those solutions will help you reuse more than 70% of the energy used to test an ECV motor. That's resulting in a highly reliable product as well as a major cost saving to your production. I hope that you've enjoyed this webinar, and Marcin and I will now be available for questions if you have any.
Perfect. Thank you, JL Marcin. Clearly, your experience in this field has been a huge asset. Marcin, can you speak to what is the maximum RPMs you could go up to?
In a current design, we think that the current design is capable of going up to 20,000 RPMs, and that is also a current trend that we observe in the market. We do receive a number of RFQs requesting higher and higher RPMs, and they all oscillate within that 25,000 RPMs. Of course, in this case, the sensitive element of the system should be redesigned or replaced, such as clutch and the motor, of course. But certainly, in our experience, that seems to be possible. If you do have a requirement like this, let's discuss it in detail.
Perfect. And Marcin as well, what is the minimum takt time of the functional test solution?
Well, that really depends on the set of tests that needed to be executed. In the very case, what was influencing the takt time in our case was, for example, filling in and removing the coolant from the DUT. So prior to testing, the coolant must be injected into the DUT and the circuit must be closed. And that operation itself can take up to a few minutes. So everything depends on the test specification and on the actual design of the DUT. So at this point, it's hard to tell. In our very case, the takt time of the solution was about 7 to 8 minutes.
Perfect. JL, I think this one will be more for you. Someone mentioned that they work for a company that requires building similar models in different regions. How would you go about supporting that?
Yeah, I guess that's a request we've seen often. People have to build in localized regions in the Americas, in Europe, or in Asia. So we've built a delivery process that enables us to do that. Of course, with the different offices that we have, we're well positioned to have engineers in all locations. But on top of that, we've developed support programs with service level agreements that help to manage a certain response time. We have partners also in regions. If it's in an area where we don't have our feet on the ground, we've developed partnership with other companies that we've been working with for years. And finally, with COVID coming in, we've seen a lot of people requesting remote support. And in the case of remote support, we've tried all the new different technologies with AR goggles and remote connection, and it actually works really well. So that's also another way that we've improved our capability to deploy and support globally.
Thanks, JL. I have a few more here. Would it be possible to redesign the power circuit so that it's based on Li-ion battery that is discharged by one motor and charged back by the other?
I think I'll take that one. that is an interesting concept, and at first, as a first thought, we actually thought about it. We thought that maybe that's gonna be way to or the direction to go to, but then we must remember that the energy draw from the battery in a certain period of time is much higher than the energy absorbing capabilities of the battery. So in our case, when we would supply energy from the battery to the DUT, for example, and then drive the tester's motor that generates the energy, the energy generated by tester's motor couldn't be easily directed into the battery. Only portion of that energy could be directed into the battery, because simply battery through its chemical construction cannot absorb such high amounts of energy. So naturally, part of that energy would go into the battery, but the other part would have to be wasted and dissipated in some form of heat, for example, so just dissipated in resistors. I think that concept would work, but definitely an overall efficiency of the solution would be less than what we achieved with the battery simulator.
Great, thank you. And I have one last question here. What other test systems do you build for the EV segment?
I'll take this one, Martin. So yeah, the EV segment could be seen as quite large, but you know, we mentioned earlier in the webinar that we did tests for the charging stations, so that's something we've definitely had to do. We've had to do the battery management system tests, power steering tests, and we've done you know, solutions for the braking systems, which are slightly different than a conventional cars because of the energy recirculation. And finally, you know, anything that pertains to infotainment testing is something that we've touched, as it brings a lot of value in those electric cars with respect to user experience. So yeah, it's a wide range of capabilities that we had to test. But as we mentioned, I think the energy motor, the tester motor, is one of the latest solution that we've been able to bring to market. So.
That's wonderful. Thank you both very much for your time, and to everyone attending. We really appreciate your presence here today. And if you're looking for more information on EV testing, please don't hesitate to reach out to Averna. We hope everyone enjoys the rest of their day. Thank you.
Thank you, everyone.
Thank you very much. Bye.